Okay. So, so all these things we have derived, right, whatever has been given here, whatever has been given here. So, all these things here derivation were not given. So, I thought I should derive it. Only thing is that it is on the your writing actually that your your this pen is little bit thicker, but I hope you have understood. You can easily do it of your own, right. So, this is I told you synchronizing coefficient, and therefore, delta p ti 1 2 also we derive 2 pi t 1 2 of this one, right, and similarly delta p ti 2 1, and finally, your t 2 1 also we have derived and we have given that, right. Now, P r 1 and P r 2 I told you the area capacity ratio, and the division also delta p ti 2 1 I told you is equal to A 1 2 delta p ti 1 2, this already we saw, and A 1 2 we call area capacity ratio, that is minus P r 1 upon P r 2, we take the minus sign. Otherwise, if you take only A 1 2 is equal to P r 1 upon P r 2, then this will be a minus sign, that is all, nothing else, right. So, with reference to equation 10, now if you look into this, earlier also we have seen for isolated system, just hold on, for isolated system, what we have seen that your it was only delta P g minus delta P L 1 is equal to only this much, because this was not there for isolated system, because there was no tie branch, right, there was no tie branch. Now, that your what you call, you have the tie branch. So, for example, this is your generator, right, and this is your tie line, that is 1 2, this is 1 and this is another this is generator 1, generator 2, or area rather area 1 and area 2, right, and this is 2, and power is flowing here, that is your what you call that your P tie 1 2, right, delta P tie 1 2, suppose change, right, and some load is also there. So, generation has to match the load and this tie line power. So, in general equation should be that area 1 say delta P g 1 minus delta P L 1 minus delta P tie 1 2 is equal to 2 H 1 F 0, then d dt of delta F 1 plus d 1 delta F 1, right. So, because generation has to match this your what you call that load plus the whatever going to the load and what was power flowing from 1 to 2, right. So, in that case, and loss is neglected because resistance is not considered. So, same equation, that means delta P g minus delta P L 1 is equal to, this is already we have seen that because of that transient imbalance, right, plus this minus delta P tie 1 2 brought to the right hand side, that is all, right. Now, with this, if you take the Laplace transform and simplify, right. So, you can write or what you call this is one equation. Now, Laplace transform equation 27. So, we know that delta p tie 1 2 and delta p tie 2 1 both are known, right. So, and this is just one thing, this page, that page 32 actually repeated once, right, this is 32 and this is also 32, right. So, this page again do not read, this page you skip, right, because already we have discussed this page, you just skip this page 32, because twice it has been scanned twice, right. So, this one you skip, and then we will go to the page 33. So, now if you take the Laplace transform of that, so delta f 1 s will be delta p g 1 s, again and again I will not put s because it is understandable, minus delta p l 1 s minus delta p tie 1 2 s into k p 1 upon 1 plus s t 1. The way we simplified for isolated system, here also you do that, right, whereas for area 1 k p 1 will be 1 upon d 1 and t p 1 will be 2 h 1 upon d 1 f 0, right. So, this is equation 28 and this is equation 29. So, block diagram representation of equation 28, then equation your what you call 28, this can be given as, so it was actually it was delta f 1 s is equal to delta p g 1 s minus delta p tie 1 2 s minus delta p l 1 s into k p 1 upon 1 plus s t p 1. So, this is delta p g 1 s. this is delta p always, this is a plus sign minus, and this is your delta p tie 1 to s into this into kp1 upon 1 plus stp1 is equal to delta f1s. So, this is the block diagram representation. So, for isolated system this was not there, but now it is interconnected to another area. So, that is why this tie power flow also you have to account it, right, we have to put it. So, similarly for area 2 you can make it, this is delta Pg2, this is delta minus delta PL2S, and this is actually your delta P tie 2-1, right, that is actually nothing but A12 delta P tie 1-2, that is we have put yes because of we have taken putting in terms of Laplace operator, right, but this is actually delta P tie 1 is equal to A12 into delta P tie 1 to S, that is why it is written A12 is this one, right, into Kp2 upon 1 plus STP2. So, this is that block diagram representation of the your what you call of the power system side. Now, if it is so, then if you make the complete block diagram for two area system, another point is the tie power. So, we know that your delta P tie 1-2 that we have seen is equal to 2 pi T12 then integral of del f1 dt minus integral of del f2 dt, right. So, if you take the Laplace transform on both sides, so because of integration this thing, so it will be 1 upon s. So, 2 pi 212 upon s into delta f1s minus delta f2s. So, this is equation 30. So, tie line power flow, small perturbation tie line power flow model, well also your what you call can be obtained using Laplace transform, right. So, therefore, this is your from the for this equation 30, this is the block diagram that delta P tie 1-2 S is equal to 2 pi T12 upon S into delta f1 S minus delta f2 S, I mean this equation 30, right. Therefore, the total complete block diagram of two area system it is like this. Let me just reduce its this thing, just hold on. So, this is actually your what you call that block diagram for two area interconnected power system, right. So, in this case if you look, there are 7 state variables. This is say x1 that is delta f1, x2 I have marked delta f2, and this is x3 that is your delta P tie 1-2, right, and this is x4 is delta Pg1, x5 is delta Pg2, x6 is delta E1, x7 is delta E2, right, and this is your U1 and U2, this is coming from supplementary controller that will be seen later, and this side minus 1 upon R delta F1 and this side minus 1 upon R2 delta F2, and this is the load disturbance delta PL1, all part by part we have seen, now we have combined together, right, and this is delta PL2 and this is that your A12, that is this is actually delta P tie 2-1, right, and this is that this portion is the your what you call tie line modeling, right. So, and this is that two area system, but without and U1 U2 is coming from somewhere later we will see, right. So, this is two area your what you call block diagram model, right, and you have 7 state variables. So, when you write the equation x dot is equal to Ax plus Bu plus gamma p, right. So, you have 7 state variable. So, A matrix will be 7 into 7 matrix, right, and B will be there are Bu. So, 2 inputs are there for B. So, B will be your 7 into 2, right. So, and 2 and P is the disturbance matrix. So, this is PL1 and this is PL2. So, 2 disturbance is there. So, P actually will be your 7 into 2 matrix, right. So, this will be, and you can easily write now all the state variable equation x1 dot, x2 dot, all these things. So, I am giving you in the complete matrix form, but you can easily write x1 dot, x2 dot, x3 dot like this, right. So, So, if you write this, so this is actually your what you call, that is your x1 dot, x2 dot, x3 dot, x4 dot, x5 dot, x6 dot, x6 dot and x7 dot, right. And x dot is equal to A, this is your A matrix, this is 7 into 7, this is your A matrix, it is 7 into 7, this is x1, x2, x3, x4, x5, x7. So, this is Ax, x dot is equal to x Bu plus gamma p, I will show you. So, when you write that this equation, you will find that for x3 that diagonal element is 0, but all diagonal elements are negative, right. And similarly, this you can easily make it of your own. I am not making it here, otherwise it will consume lot of time, right. And next is your Bu. So, this is my B matrix, this is our B matrix, this is our B matrix, this is 7 into 2, right. And this is your gamma matrix, right. So, gamma p, so this is gamma matrix, right. So, this is 7 into 2, not p, previously continuously recording. So, I thought I made p 7 into 2, it is gamma matrix, because equation is x dot is equal to Ax plus Bu plus gamma p, right. So, it is a gamma matrix and p is nothing but PL1 PL2, right. So, this is 7 into 2. So, this is your equation, right. Now, where A is 7 into 7 matrix, B and gamma are 7 into 2 matrices, X, U, P are state, control and disturbance vector. So, this is transpose, X transpose is equal to x1 through x7, it is given, U transpose U1 U2 and P the disturbance vector, that is delta PL1 and delta P2, right. Now, the steady state frequency deviation is the same for the two areas, right, when it reaches to a steady state. So, at steady state delta F1 is equal to delta F2 is equal to delta Fss, right, and ddt of delta F1 is equal to ddt of delta F2, right, is equal to 0, because at steady state all the derivative will be 0, right. So, if we come back to this equation, right, if we come back to this equation, if you come back, then you will find that at steady state at this term will be 0, right. For area 1 this term will be 0. So, delta Pg1 minus delta PL1 to H1 upon F0, that means this term is 0, means this term will not be there, but other things will be there. Delta Pg1 steady state minus delta PL1 is equal to d1 delta F1 steady state and delta Pti1 2, but this term will be 0. Similarly, for area 2 also ddt of delta F2 is equal to 0. If it is so, then this equation we can write delta Pg1 steady state minus delta Pti1 to steady state minus delta PL1 is equal to d1 into delta Fss. The delta Pti1 to Ss from right hand side it has brought to the left hand side. So, this is equation 34. Similarly, for area 2 it will be delta Pg to Ss minus A12, because delta Pti21 is equal to A12 delta Pti12. So, delta Pg to Ss minus A12 delta Pti1 to Ss minus delta PL2 is equal to d2 into delta Fss, right. And another thing is that a steady state delta Pg1 Ss will be minus delta Fss upon R1 and delta Pg to Ss is equal to minus delta Fss upon R2. That means, this block diagram actually what we are doing is that we are first considering the system is uncontrolled, that means U1 is equal to U2 is equal to 0, right. That thing first you have to see this, right. And second thing is, I told you one technique that regarding your putting your what you call that t tends to infinity, s tends to 0, but here you cannot make it, right. Here you cannot make it, but in general that your steady state error, that delta Pg1 Ss, that is your delta Pg1 steady state is equal to actually minus delta F1 steady state divided by R1. This is known to us. Similarly, for delta Pg2 Ss, right. So, if it is so, I mean if you draw your what you call your steady state block diagram, then all the steady state value you have to make it, right. So, that is why in this case your that delta Pg1 SS, right, is equal to minus delta F SS upon R1, because at steady state that your delta F1 SS is equal to delta F2 SS is equal to delta F SS, right. So, that is why you have written minus delta F SS upon R1 and this is minus delta F SS upon R2, right. So, now if you solve this equation for delta F SS and your delta P tie 1 to SS, put all this one you put it here and this one you put it here and you solve it right. So, if you solve it, then you will get delta F steady state is equal to A12 into delta PL1 minus delta PL2 divided by D2 plus 1 upon R2 minus A12 into D1 plus 1 upon R1. Similarly, delta P tie 1 to SS you will get D1 plus 1 upon R1 delta PL2 minus D2 plus 1 upon R2 delta PL1 divided by D2 plus 1 upon R2 minus A12 D1 plus 1 upon R1, right. So, sometimes what we do before moving further, we define that area frequency response characteristic, right. Earlier we make beta is equal to D plus 1 upon R. This is called FRC, AFRC, area frequency response characteristic, right. Therefore, for area 1, this one and this one we can write that beta 1 is equal to D1 plus 1 upon R1, right. Similarly, we can write beta 2 overwriting on it, beta 2 is equal to D2 plus 1 upon R2, right. So, this is beta 1 and this is beta 2. So, that means this delta FSS, I mean this equation delta FSS I am writing here delta FSS, it can be written as your numerator A12 delta PL1 minus delta PL2 divided by this is beta 2 minus A12 beta 1, right. And similarly, for tie power this one it can be written as your beta 1 delta PL2, right, minus beta 2 delta PL1, right, divided by your beta 2 minus A12 beta 1, same thing, divided by your beta 2 minus A12 beta 1, right. Now, if for example, if A12 suppose load disturbance has occurred only in area 1, right, and your what you call and delta PL2 is equal to 0, say delta PL2 is equal to 0. For example, for this thing, suppose load disturbance has occurred only in area 1. So, keep delta PL1 is equal to delta PL1. There is no load disturbance area 2. So, make it as a 0 and say that both the areas have equal your what you call at your equal your area capacity. That means, A12 is equal to minus PR1 upon minus PR2, and if PR1 is equal to PR2, then this will be actually minus 1, right. So, if it is so, if for this condition if A12 is minus 1 and delta PL1 is there, but delta PL2 is 0, then right, then you can little bit let me this thing, right. Therefore, this one you can therefore, delta FSS will be then your delta just hold on, delta FSS will be delta PL2 is 0 and A12 is minus 1. So, it will be delta PL1, right, divided by your this is B2 and A12 is beta 2 and this is your A12 is minus 1. So, basically it will be B1 plus beta 1 plus beta 2 minus delta PL1 divided by beta 1 plus beta 2. Similarly, for this one also, if delta PL2 is 0, then this one will be minus beta 2 then delta PL1 divided by your here again beta 1 plus beta 2. So, both the cases denominator is same, right. When area capacity ratio we are taking same, right. So, next we will move to this thing. Now, another thing is there that before moving further I will go to that block diagram, right. So, this is actually again I have to reduce the your what you call that size, right. So, so in this case what will happen that this A12 area capacity ratio, right. So, in that case it plays a significant role. What is this? That we know that A12 is equal to minus PR1 upon PR2, we write this way, right. That means PR1 is equal to your minus A12 into PR2, right. This is the your this is the thing. So, or suppose for example, just for example, suppose my PR1 is equal to say 8 point sorry, just suppose A12 is equal to minus PR1 upon say PR2, right. Now, suppose my PR1 upon PR2 is equal to say 8.0, right. This is the ratio. This is the ratio. That means if that means my A12 is equal to minus 8. That means PR1 is equal to 8 times PR2. That means if PR1 is 100 megawatt, sorry, PR2 is 100 megawatt, then PR1 will be your 800 megawatt. So, if you go on increasing this ratio, suppose 1, 2 like this, if you go on increasing, then what we will observe? As we will go on increasing and for a and give a load disturbance here, a step load disturbance here, right. So, what you can observe it that through the simulation only you will find there will be deviation and frequency area 1, but as this ratio will increase, go on increasing, you will find that other area deviation is very small compared to the area 1, almost flat, right, almost flat. That means if delta F2, I mean if area capacity ratio increases continuously, that means area capacity ratio increases means that for this case the way we have taken that your what you call that your PR1 is higher than your what you call much higher than your PR2, then in this case you will find for a load disturbance here you will find that your this frequency deviation will be there in area 1, but area 2 you will find it is almost flat. I mean delta F2 is almost very negligible deviation, and go on increasing it will happen that at that time what will happen, the area 2 basically will act like your infinite bus, right, because it is because frequency deviation is constant, frequency is constant, right. So, in that case there will be that means this two area system can be called as it is single area connected to an infinite system, because capacity is your what you call capacity of this area is very high. Just reverse is also possible, reverse is also possible. Suppose if you make PR1 by PR2 is equal to 1 upon 8, in that case what will happen that your area capacity of this area is very high. So, if disturbance occurs in this area, then you will find this side frequency deviation is negligible compared to this one. So, this side will act as an infinite capacity, right. You can verify it through the simulation and this will happen, right. So, and at that time system may be considered as that your what you call that your single area connected to an infinite capacity system. That means in this case if it happens so for higher value of A12 ratio, then this part need not be considered for the simulation, because this is actually your what you call there will be almost no deviation in system frequency. In that case this part should not be there, this part should not be there. That means in that case 1, 2, 3 and 4 there will be 4 state variables, right. So, this is something interesting. So, you can verify through simulation that this will happen, right. So, we will go to now that regarding that area control error, right. So, tie line frequency bias control we call. So, equation 38 and 39, I mean these two equations, steady state error of frequency and tie power deviations suggest that there will be steady state error of frequency deviation and tie power deviation, right, following a change in loads. To correct those steady state errors, supplementary control must be given in both the areas, right. The supplementary control in a given area should ideally correct only for changes in that area. I mean, suppose integral control area, suppose you have integral controller in area 1 and area 2, if there is a load disturbance in area 1, then that controller in area 1 must correct that frequency deviation of its own area, right. So, in other words, if there is a change in area 1 load, there should be supplementary control action only in area 1 and not in area 2. Therefore, equation 38 and 39 indicate that a control signal made of tie line flow deviation added to frequency deviation weighted by a bias factor that we will see would accomplish the desired objective. This control signal is known as area control error. So, area control error basically it is a function of frequency deviation and tie power deviation, right. So, the area control error for area 1 and area 2 can be defined as say AC1 is equal to B1 into delta F1 plus delta P tie 1 2, this is equation 40, and AC2 will be B2 delta F2 plus A1 to delta P tie 1 2, that is equation 41. So, B1 is equal to beta 1 is equal to D1 plus 1 upon R1 and B2 is equal to beta 2 plus is equal to D2 plus 1 upon R2. So, beta 1 beta 2 are the frequency response characteristic or area frequency response characteristic of area 1 and 2 respectively, right. So, thank you very much, we will be back again.